Thank you all for attending this month's webinar, The End of the Cloud as We Know It. We had to reschedule, but fortunately, Matt was able to make it this month, and I promise it was worth registering to this reschedule. So today with me, I have Matt Terifiro from Vapor.io, and I'll let Matt introduce himself, and then I'll take it back from him right after that. Matt?
Yeah, sure. So again, my name is Matt Trefiro, and I'm the Chief Marketing Officer of the edge infrastructure company, Vapor.io. Today, we're working primarily in the United States, but we do have global ambitions. We deploy networks in micro data centers and software-defined networks very close to the edge of the access network to deliver a more performant internet to support these low latency use cases. We're building out in parallel in 36 cities in the U.S. And when we're done, we will be within a few, maybe a few hundred microseconds from most of the population of the U.S. And I'm also the co-chair of the State of the Edge project at the Linux Foundation, and I have a podcast called Over the Edge, which is focused exclusively on edge computing.
Cool. Thank you, Matt. So today we're going to address something that's very important. So a lot of you guys already know what edge is. We talked before about the spectrum of the edge and the fact that the edge is the spectrum that is all around us, depending on how you see it. Does it start from the cloud or not? I personally don't see it starting from the cloud, but the cloud could be an optional endpoint for data that could be stored for a long period of time. That said, one of the reasons you need to have edge computing is latency, and Matt will kind of like deep dive into the latency issue and why it matters today, and matters even more tomorrow. And I'll let you, Matt, take it from here.
Yeah, before I dig into latency, I wanted to address the insertion of a little commentary about cloud versus not cloud, which I think is actually pretty pertinent and interesting.
Sure.
So you look at the general principle of edge computing, and it's fairly simple. Without getting into the weeds, it's about moving the compute and storage closer to the point of use, right? And where that tends to be today is not where most of the cloud exists, which is in the core of the internet, in these giant hyperscale buildings out in the middle of nowhere owned by Amazon and Microsoft and Google. It tends to be where all the interesting stuff happens: on our car, on our devices, in our factories, in our hospitals, in our retail stores, on our streets. And there are a set of applications. In fact, largely the way we see the future will be very dependent on these applications that want to interact with the real world, and they want to interact with the real world on essentially real time, so that whether it's the car that's going to crash or the autonomous drone that needs to land, or it's the traffic flow stoplights that you need to coordinate, or the factory robotic arm you need to move, we want to have the compute near these devices so that it can be controlled. They can be controlled in real time. So time is really important here. So whether you are producing the compute from that which looks like a cloud, whether it's an on-premises cloud, if I'm running a Kubernetes stack, I have a cloud native foundation, so it's a cloud by some definition. And whether that cloud is owned by me, or it's owned by Amazon, or owned by Microsoft, and whether it's on my facilities or 75 microseconds away or 100 milliseconds away, it can all be looked at as a continuum from the device to wherever the rest of the compute and storage is. And the way I'm seeing applications being architected, it actually spans the entire continuum. You have some of your services running in the core because they're not time sensitive. You have other services that are running closer to the device or even on the device because they're super time sensitive or life critical or something. So first, I just kind of want to set out that concept. Now, my personal belief is the most interesting edge applications are going to merge when the thing we call the internet actually gets to the point that it can deliver services in near real time. Because the internet, which is kind of a synonym for cloud in many ways, it has immense amounts of compute and storage. It's close to infinitely scalable, and it connects everything to everything else, right? So, for example, if you're trying to build a smart vehicular system of whatever kind, you're going to be able to build a better system if you have access to data that you can't see from the car. So what's happening around the corner? My LiDAR can't go around the corner. What's happening a mile away with traffic flow? Is there an accident? And so only the cloud, only the internet can actually reasonably gather all that information in close real time to provide decision support. So that's why I believe that the internet is going to be ultimately the best way to deliver edge. It's just going to become the internet. We're going to stop talking about edge. It's just going to be the internet. That's my personal belief. And we can talk about
yeah. I mean, Matt, I think that's exactly like how I personally see it. Like I mean, the edge, originally and is still defined as a spectrum or the continuum that you are talking about. And actually edge computing or CDN existed before the cloud, historically speaking. Mm-hmm. And I think, having like compute everywhere and data being generated everywhere, and that's and consumed all over the place. That's really what the internet will become, kind of like a digital era, referencing the Avatar movie.
Well, I mean, really, if you look out, say, a decade, right, and you say, okay, where is this going? How's it going to benefit society? Well, there's a couple things. One is the internet began as an information delivery system, and it delivered that information primarily to humans, right? So even CDNs were designed to cache rich content, so large images at the time, because we still were using dial-up mode in some cases, but increasingly digital movies and things like that, so that a human can have a near real-time experience at human scale. Humans think and operate in ones of seconds, right? And that is glacial to a machine. Machines operate in nanoseconds and microseconds and milliseconds. And the internet we're moving to is a service delivery internet. And most of those services are going to be delivered from machines to machines at machine scale and machine speed. And the internet we built does not support that today. It wasn't built for that. It was built to deliver content mostly downward to the device. But if you look 10 years out and you assume, okay, let's solve for that infrastructure problem where you've got you have more than a best effort internet. You've got a very discrete, predictable, time sensitive internet. What are we actually going to see? Well, I think what's going to happen is we're going to essentially build what amounts to a digital twin of the world. So we're going to have a view of a city that has every stoplight, every sensor, every security camera, anything that's capable of producing data or taking an action, and we're going to build a model of it. We can do this today with like weather systems, right? So it's certainly possible. We're going to build a model of that city or that place or that factory, and it's going to be a digital twin, and we're going to run algorithms, deep learning algorithms, inferencing, to bake predictions and then to create actions that respond to those predictions or affect those predictions. And in order to do that, you need access to massive amounts of compute and storage but ultimately we're going to be able to do just really magical things with our world once we've built these models that we can run these simulations on and make intelligent decisions about. Okay, so let's talk about latency. All right, so yeah. You want to talk about latency, or do you want to make another comment?
No, that's pretty good subject. I mean, it kind of like goes in line with what we had as kind of like content for previous webinars, especially the previous one around smart cities. We talked a lot about digital twins, and I really think, I personally think that digital twins are technology that is necessary to enable like a global intelligence. And if you look at it from a if you compare like a distributed computing paradigm with sensors all over the place, and also actuators all over the place that can make actions happen, it really, when you compare it to a biological model, which is the brain, it's very similar. And that digital twin is basically the illusion that the brain gives us about the real world. Like when I'm looking at my screen, I see colors. That's an illusion, right? And I see HD, and that's an illusion. We don't really see HD. Our eyes do not have that capability. It's an illusion that the brain creates, a virtual twin of the real world, and that's basically that's pretty cool, actually. And
well, and if you really step into the future and you believe, like what Zuckerberg believes about the metaverse, we are going to be able to step into that digital twin in the form of virtual reality glasses, which is really interesting. The ability to interact with a representation of the real world, whether it's because you're playing a game or you're learning how to do something. Imagine learning how to repair a jet engine without actually having to touch a jet engine, or even better, imagine learning how to do brain surgery without actually, taking the risk on hurting someone's brain. And of course, this is very futuristic stuff, but this is the path we're on, and there are applications that can be delivered today. Roboticizing a factory can be delivered today, that we can start improving the ability for that capability to be delivered over the internet. So let's talk about latency. Let's just talk about like a robotic arm. Okay, and I'm going to oversimplify this, and I'm going to generalize. But let's say that in order to properly manipulate the robotic arm in the way that you want to, that you have to control its servo motors in less than 1 millisecond. And that's an arbitrary number, but that's a realistic number, 1 millisecond. And the way that's been done historically is you actually have a computer on the robot. And because it's actually on the robot, the speed with which it can communicate to the motor and communicate to the CPU and communicate to the motor is about as fast as the motor can move, probably faster, right? So there's plenty of time. But now you've got this machine that you have to deal with, and how do you upgrade it? And what if there's not a new compute for your new algorithm? And it's isolated, it's an island. And so, as we've done with almost everything in our life, we've started to connect it to a network. All right. What the network allows us to do is it allows us to separate the compute and storage from the device, the thing, and the next step is that network could connect to the internet, because the internet's just a network of networks, right? And so now that we've got this space between these, this physical space, right, we have to worry about, well, how long does it take the signal to get from one location to another? And what are the limitations, right? So the primary limitation is the speed of light. That is our upper bound, or lower bound in terms of low latency, or upper bound in terms of speed, right? We can't travel fast. Nothing can travel. I mean, maybe I don't know enough about quantum computing, but nothing we think of, at least in realistic terms about how we use the internet today, can travel faster than the speed of light. And you think of the speed of light as being just so fast it doesn't matter, but computers are so fast the speed of light actually does matter. So to sort of give you a very practical example, the speed of light travels takes about 3 microseconds to travel a kilometer. So you can kind of do the math, and that's through no medium. That's in a vacuum. That's in a absolutely perfect scientific situation. In a vacuum, if you've got like a single mode fiber refractive index of like 1.5, you're going to have the light isn't going to go straight. It's going to bounce off the walls, the mirrored walls of the thing, and it's going to be about 5 microseconds to go a kilometer, which means that you can go about 20 kilometers, or for those in the US, 12 miles in about 100 microseconds. All right. Now, 100 microseconds sounds like a tiny amount of time, but there's actually applications that require 100 microseconds of one-way communication latency. Okay, so if I have a theoretically perfectly piece of fiber, and and my compute is instantaneous, and I need 100 microseconds one way, I theoretically could locate the compute up to 20 kilometers away from the thing I'm controlling. And in fact, that's what we're doing with virtualized 5G RAN. So the radio access network that represents the new 5G rollouts, there are configurations that are where the parts of the radio access network are virtualized. And there's only two parts you really need to think about. One is the radio head, which is the thing that sits on the tower or the pole and sends the radio waves out, and the baseband unit, which used to be an appliance, but increasingly is being turned into software that runs on white box, AMD and Intel and ARM boxes. And in order to control a 5G radio, the baseband unit, the software that runs the baseband unit, has to be about 100 microseconds or less from the radio tower. So in order to build the infrastructure to drive a 5G network through virtualized software, you have to have something that looks like a data center with something that looks like a fiber route that's 100 microseconds from every tower. And if you don't hit that latency number, you're not going to be able to control the 5G RAN. So that's just one example. And every possible use case, whether it's controlling an autonomous drone, a robotic arm, or a laser lathe, has a latency budget, a tolerance within which you can do. And some have more tolerance, and others have less tolerance. But really, this internet that used to be about delivering content and today is still largely quote unquote best effort, can't drive something that requires that kind of tolerance, because best effort is not good enough. You need a discrete, predictable timing from the compute to the actuator, or from the sensor to the compute, in order to do that. And so we need to re-architect the internet to deliver these new kinds of latencies.
Cool. So that's from the latency perspective. I mean, obviously, that's only what takes information to travel. There is also another side of it, is like generally, like if you go to a central location, I'm referring to any centralized model, and the cloud is the number one centralized model, you're gonna have a queue waiting in there, because it's not only one connection. So there is another aspect on the other side.
Absolutely. Yeah, and in fact, when we were talking earlier, I was, I'm on this crusade to dispel all of the mistakes the industry makes. So latency is really important. Sometimes it's not as important as someone wants you to think it is, and sometimes the number they're quoting is not what you think it is, and maybe it's not even what they think it is. And I'll give you some examples. So you have to ask yourself, when somebody says, okay, I need to do this in 1 millisecond. All right, first of all, do they mean round trip latency? That's a 50% error if you don't actually specify whether it's one way or round trip latency. And then, is it just the communication latency? Because on the other end of the communication, you've got a compute stack that has to do something, has to run an inferencing algorithm on it. And so almost everybody I've talked to in this industry, I mean, from the companies that are delivering the equipment to the infrastructure, whatever, get all of these things confused, which is really surprising to me. So somebody might say, I need a 75 microsecond latency. And what they mean is they need 75 microseconds of one-way connectivity, so that they can add another 700 microseconds of stuff on either end, like the handshake that the 5G modem needs and the compute that I need to do. So that 75 microseconds is just about the bits in the glass. It's not about anything else. So you have to be really clear about that. And then also you have to recognize the difference between like reality and hypothetical. right? So there's a company that shall remain nameless, and they're not the only one that does that, but they go around touting we are, and I'm making this number up, we're 3 to 5 milliseconds from every business on the planet. And well, first of all, again, is it one way or round trip? And are you counting the computers or just connectivity? And then how are you going to deliver that? Because you don't have a perfectly straight piece of glass that goes from your optical gear in your building straight out to that business. Because that's the only way you're going to get that perfect, say 5 milliseconds over, a couple hundred kilometers or whatever it is. And what actually happens is there's, potentially 3-4 network hops. The fiber never goes straight because it's laid down rights of ways on train tracks and stuff. And so you end up with kind of a meaningless number, right? It's like a marketing number. It's not a real number. And so I think, as all of us are looking to really understand what one product does versus another product, or what we might need for our applications, we have to ask those questions. Is it theoretical or is it real? I mean, have you actually tested it? Do you actually get that latency or not? And then how do I get that latency, and how guaranteed is it? Because again, it's not just about, so we're moving this world of service delivery, but there's also quality, there's quality assurance on that service delivery, right? Like, how predictable do I have that delivery latency? Because if I'm trying to control a drone, maybe I need, 7 nines of predictability so that I don't crash it, or, whatever the use case application is.
So, so that's from the latency kind of like side, and Matt, like we talked to, I personally talked to a lot of people, and there is one big reason they dismiss edge computing is they don't think their application is latency sensitive. Like what do you think of that? Like, do we really have use cases that are edge computing?
Sure. I mean, factory robotics, great example. I mean, so their application may not have latency sensitivity. Great. Or they may have solved the latency sensitivity by building an embedded system that sits on the device. Or maybe they've solved it by having a direct fiber run to some equipment closet that sits on the site. But there's other factors involved, right? It's not just, can I do it technically? It's, can I do it at scale? Can I do it cost effectively? And can I make it easy for the customer, right? So if I'm trying to roboticize my factory, today I have one choice, and that is I have to buy a data center, basically. I have to stick a Schneider Electric micro modular data center box in my parking lot, pack it with all this IT gear that I have to own and operate and run, right, in order to get the latency within my factory. Well, there should be another choice. You should be able to get that which looks like a SaaS service delivered that controls my robots, that doesn't require any equipment on site. So there's lots of applications, and then it's not just about latency also. So retail is a really good example. So there's a lot of really interesting retail examples, for inventory control and loss prevention with real-time cameras, and then some potentially creepy things like user tracking, but also like automated checkout, right? Where it's very clear that delivering those services from an aggregated location. I won't say centralized because it's not centralized, but from an aggregated location. I mean, I live in near Dallas, Texas, and I think there's a Walmart about every 2.5 miles. And so does Walmart, do they really get the best use of their time, energy, equipment, and so on by having a couple of racks in every single store? Or would they be better served from an aggregation location that is, within, a few hundred microseconds from multiple stores, and then maybe they have multiple of those locations, so now they get levels of resilience, right? So you're able to take advantage of some of the economies that the cloud provides because it's centralized, but you're doing it not by being truly centralized, i.e. the center of the country. You're doing it by being kind of micro-centralized through an aggregation point. So literally, imagine if you took all the racks in the Walmarts and put them in one data center that was right in the middle, and ran fiber to all of them. Well, you'd probably be able to reduce the equipment footprint by 50%, right? So there you get this huge cost savings, millions of dollars of cost savings. And you get, you can achieve higher resilience if you put 2 data centers down, because now you can run active, and if a fiber line gets cut, you can fail over. You don't have to have IT in each store. You don't have to have a rack in each store. Equipment upgrades are a lot easier. So it's not just about latency. And on top of that, it can support all the low latency applications like, doing real-time video analytics on, the 100 cameras in the Walmart store and in each Walmart store and parking lot that, is spitting out, 4K video.
Yeah. I mean, I think the model you were referring to is a decentralized model, which is basically the only model.
Well, it's decentralized, but it's aggregated.
Yeah, I know. I mean,
yeah.
I'm just trying to kind of like my thought was going like, this is a decentralized model, which is kind of like the only model that you can get going like cloud native, where you make kind of like let's take that example of Walmart.
Yeah.
Though Walmart technically is going a separate route, there's some PR and news about that. But so Walmart could have some services running locally that might process some data, and then data that needs to be processed from different Walmart could go into that central location that's nearby, or 2 locations that are nearby. And that data doesn't need to go to a centralized cloud location. Maybe only some resulting data that
that's right
they need for BI or something like that would go to the cloud, right? And that's kind of like a tree, and a tree is also a decentralized model as well. That's kind of like what I was referring to, and I think like software would need to move from the purely hub and spoke anyways, and though a lot of people do not do hub and spoke, though they think they're doing it. And the simple example is in the cloud, you have a client server architecture, which is kind of like hub and spoke, but as soon as it's one to n, and as soon as you put a load balancer, now it's an end to end or m to n. So it's not really a hub and spoke, but more like another tree, because behind those services that are behind the load balancer, you have something that is centralized, like a database, for example. But at the end of the day here, so I think the idea is a lot of use cases that we're going to see will require low latency. We know that that's the case in a lot of industrial use cases. We know that this is going to be the case for AR and VR,
mm-hmm.
and that's going to be the case for autonomous cars and most of the use cases in smart cities. But there are also other use cases that already were using edge computing, like gaming or the internet itself, and will develop or will need lower and lower latencies just because users demand better performances, right?
Sure. And again, I bring you to that distinction between machines talking to machines and humans talking to machines, right? Yeah. And gaming's actually a really interesting example because it's a lot of both, right? So in order to make it seem like it's real time, even though I'm playing with somebody that might be in Europe, the version of the game running locally is collecting data and making predictions on what's going to happen. And so if I'm moving to the left, but I haven't yet got the signal and the other guy's moving to the right, my machine will make a movement of my opponent's player to the right, predicting that that's what they're going to do. and then when they get the actual movements, they do the minor corrections. And so there's a lot of really tricky things to increase the perception of lower latency without actually increasing latency. But there's an upper bound to that, right? I mean, I have 2 kids, and they can't stop talking about their ping speed, which is the only thing they use the terminal for. Check their ping speed.
Yeah, unfortunately. I mean, at least they're using the terminal. So
yeah. But you're right. I mean, gaming is a very good example of things where it's very obvious when your latency improves. Yeah. So I think, and there's going to be applications that have a preference for lower latency, but they're not willing to pay for it, right? Or they're only willing to pay for it in off hours. And so I think one of the pieces of software middleware that's going to emerge are really sophisticated scheduling algorithms. Because again, today, if I'm building an application for Amazon, I can say, well, I want one instance to be in US West and one instance to be in US East and one instance to be here. And I can kind of like do this in my head. A human can do it at human speeds. But when you've got, 1,000 locations where you can run a workload, and where that workload runs optimally, it's changing every couple milliseconds. You can't do that by hand. You need schedulers to do that, and you want the schedulers to take in some pretty complex information, right? Like what is my latency budget? How much tolerance can I change? Because it's not just latency. Like jitters actually. It's a much more subtle concept, but jitter is actually way more important than latency. Lowering the jitter. So the jitter is the variance on, okay, the first time I send a packet, it's 1 millisecond. The second time it's a millisecond and a half. The third time it's a half millisecond. The jitter is that deviation. And while I may say I have an average of 1 millisecond latency, it might be because I have a bunch of low latency stuff, and every so often I have a spike. Some applications can't handle that spike. And so, like a robotic arm, right? You don't want to be moving the robotic arm, and then at the crucial moment that you need to make that next step, you've got a 100 millisecond spike that you have to deal with. So applications are going to specify where they need to run from a geolocation perspective, what kind of constraints they have in terms of latency and jitter and other things like that. But they're also probably going to introduce cost. So like if I'm a gaming company, I'd say, run this workload next to my users if it costs me less than, a half a penny. But if not, maybe just my premium users, the people that pay me an extra $20 a month, they get this tier of where I'm actually going to work and pay to improve the performance. And so there's going to be,
and that's the part where a DLT, or commonly known as blockchain, will play a big role in determining like stuff like that, like run it closer if it's a premium, and that may be a little like far away, but still okay if it's a free user or regular user and stuff like that, and maybe negotiating the price between machines to using a token or a coin rather than doing all of that through
I think that's very likely that the payment, because billing is hugely complex, and so if you can actually embed the payment in the request to run the workload, that's a pretty exciting idea.
Yeah. Cool. So Matt, let me see here if anybody in the audience here has any questions. You can either raise your hand. There is a little hand on the bottom, and then I'll let you know when you can ask your question, or you can put it in the chat. Waiting for the questions. I think, Matt, if you kind of like tell us a little bit about the idea behind Vapor.io.
Sure.
Which, I mean, I'm not an expert of, but in my mind, Vapor.io is putting data centers by cell towers.
I mean, that's not wrong, but it's actually more sophisticated than that. So the biggest challenge in edge computing isn't where to place the compute; it's the network that connects the compute. As I talked about, like that's where all those tolerances come in. And so what Vapor.io is built is what we call the kinetic grid, and it's based on this technology that we call the kinetic edge. And what it is, it's a combination of an optical network, the software-defined networking software on top of that, interconnection software, so the ability to cross-connect two networks to each other at machine speeds in remote locations, right? Because again, when you've got multiple networks talking to each other, today that data has to trombone out somewhere, and that takes time and adds jitter. And so we want to be able to cross-connect networks in a local market, ideally down to a very precise geography, to improve that. So we have our own interconnection fabric and software that runs. And then we have micromodular data centers where you have to place the equipment, right? And so our micromodular data centers where all the network optical routing and you know the switches and routers exist, but also our tenants, our clients, whether it's the CDNs or the cloud providers or the telcos, place their machines in what look like data center racks. They're very high density racks. So what that means is lots of kilowatts per square foot. Which again is pretty unusual in micromodular instances, which is why we design our own data centers for our own use. We don't sell them to anybody else, because we're trying to pack, you know, sometimes 35 or 40 kilowatts of equipment in a single rack, and a typical, you know, rack at an Equinix or something is probably 5 or 6 kilowatts. So quite an increase. So hyperscale densities, basically. So we go into a city. And I said, as I mentioned earlier, we're working in the top 36 U.S. cities, and we basically draw a ring around the population center. Then we identify all the land parcels that we have access to, and we have deals with lots of land companies. In fact, that's probably where you got the cell tower. One of our biggest partnerships is a company called Crown Castle, which is the largest owner of wireless towers in the U.S. They've got 40,000 macro cell towers, and then lots of other land that doesn't have cell towers on. It's got other things on it. And they're a partner of ours. And so we can go into a market, we can identify where all the plots of land are, and then we have about 180 different criteria to select, you know, like usually 20, evenly distributed. And then we pick 2 or 3 to start with. And on those 2 or 3 locations, we drop we pull the fiber in. We tend to locate these near fiber intersection routes, so not necessarily near a cell tower. We're actually more interested in being where fiber intersections are, at least to start. And we typically drop at least 2, if not 3, down, and that's so that you can have active high availability across. And then we layer our software on top of it, and that thing, this like mesh of the entire city, is what we call the kinetic edge. And then we have a long haul backbone. We built our own backbone that connects all these cities together, and that in its collection is called the kinetic grid. So we're essentially re-architecting the internet from the edge in. And you know, even though it sounds like crazy ambitious, I mean, it is crazy ambitious. It takes a lot of money. We're really well funded. But to some extent, this is what the hyperscalers have already done, but they've done it from the core out. Every hyperscaler runs their own backbone and has their own POPs. And the reason they do that is because they want to be able to control the performance of the network. And so we're basically filling that gap that exists today, which is this middle mile, which is from the edge of the access network to the regional IX point. It's not a very good network there, not for real-time things. And so we're making it real time, and that's our business. And so we're as I said, we're live in 6 U.S. cities today, and we're building out 36 in total right now.
Okay, so Matt, we have a sort of question here from.
Yeah, I see it. Yeah, go ahead, read it.
So I'll just condense it to what I think the question is here from what you talked about before. So I think like the general idea that came up is that the end of the cloud means that we're redesigning the internet to be a low latency, high speed, kind of like evolved version of itself. Is that what the end of the cloud means for you, or is it something else?
Well, I mean, the end of the cloud, it's not the end of the cloud. It's the end of the cloud as we know it, right? So there's a little bit of a cheat there, and the title's a little clickbaity. You know, the history of the end of the cloud meme, though, goes back to Andreessen Horowitz, Peter, I can't remember his name. He was on my board in my last company. I can't remember his name. But he had a very popular presentation that's fun to go back and watch on YouTube called The Edge is Eating the Cloud, I think, or The End of the Cloud or something like that.
Yeah, it's called The End of the Cloud, yes.
Yeah, and so the basic thesis originally was there's going to be so much compute out at the edge. Why are we going to need the centralized cloud? Now, Peter doesn't actually believe the centralized cloud is going to. Nobody who actually is in this world believes the cloud is going to go away. It's going to evolve. So today, the cloud, what is it? Well, it's a way that you can purchase resources on demand to run in a facility that somebody else owns as a service. That's essentially the cloud. I mean, you can have a private cloud and it's, in cloud native applications, but that's kind of what we think of the cloud. And it is actualized over the internet. Because it's largely centralized, it has constraints. Most of the network, or a big portion of the network to the destination, is best effort. It's not predictable. It might take 100 or 150 milliseconds to get from the device to the server and back. And so the cloud today, as it's currently architected, cannot deliver the applications of the future. So we have to re-architect the cloud, and the cloud is dependent on the internet, which is the networks and facilities underneath it. So we have to architect this thing from the dirt up, so that the cloud can extend all the way to the edge where the devices are. And that's what's going to happen. You're going to be able to run an Amazon or a Google or a Microsoft workload in close proximity to the device that you need, with guaranteed quality assurance on the network side.
Cool. So I think you have another question. So what does this mean for facility building owners who are dreaming of getting MNOs on board to deliver neutral host or better serve their tenants?
I think that's a great question. All right, so let's for the audience who doesn't know what this means. So especially with 5G, the millimeter waves don't go very far. They don't penetrate trees or walls or things like that. And so the way you solve that is you put lots of little microcells up. And so instead of a big tower, you've got like a little thing that looks like a Wi-Fi transmitter. And in a building, so imagine I'm a CBRE or something, and I own a big building. I have a bunch of tenants. My tenants want service. It's even just cell phone service, let alone like cool new applications. And the way that you did that in the past is every provider would come and hang radios. And then there was this evolution they called DAS, which is, I won't go into it, but there's a way to kind of aggregate some of that so multiple providers can use the same equipment. So in answer to this question specifically, so neutral host is this idea that I can pay, me as a third party, a building owner, or maybe a partner of the building owner, I can pay to install radios and fiber in my building for distribution of what amounts to the radio signal. And because I own it, it's mine. And because I offer it to anybody who wants to use it, it's a neutral host, meaning Verizon can use it, or AT&T can use it, or whoever wants to use it, they have to pay me, but they want to use it. So in answer to Brian's question, I think it's an awesome opportunity for in building neutral hosts. And the way that what I'm talking about is going to help you is with this disaggregated RAN that I talked about. So you're going to be able to run all the brains of the telco network. Well, the telco is going to be able to run all the brains of the network in a location that isn't at your building. They're not going to have to stick a rack of equipment or BBUs in your building. They just need a fiber network that connects to your building, and some software to do the right interconnection, so that they've got these virtualized BBUs that are running on, in data centers like the ones that I build, over a network like the one that I built that connects to your building, and they can now control the radio heads. And now the new radio heads, they can transmit over multiple spectrum. So all of the providers can use whichever spectrum they want or own, or maybe unlicensed spectrum like CBRS, over the radios that you own, and they'll either pay you to do that, or you'll do that you'll offer it to them as a service to your tenants. But I think the neutral host in building is pretty exciting. I also think neutral host out building is pretty exciting, but that's going to be harder for the large MNOs to digest.
Cool, cool. Thank you, Matt, for the answer here. I didn't know about this concept of neutral host. It sounds interesting.
It's economically so powerful. I mean, the reason, so
Yeah.
you can't just, it's not just about latency technology. It's about how much does it cost, and how easy is it, and
Yeah.
the ability to run to have multiple carriers run over the same equipment simultaneously. Shared infrastructure, the economics of it are just massive. I mean,
Yeah.
you want to know how 5G is going to be rolled out? It's going to be on shared infrastructure. That's the only way it's going to get as dense as it needs to.
Yeah, and it kind of fits on into that model of kind of like a digital real estate. Like every deployment of compute or cellular out there is basically also a digital kind of real estate asset that you can monetize, right?
Yeah, and you want it to be multi-tenant because that's how you get high utilization.
Mm-hmm. Correct. Yes, correct. Cool, cool. Yeah, I think we're a little bit over time here. So, Matt, thank you for being our guest today. That was great. Thanks to everybody who attended, and then we'll see you next month with another guest and another subject, and we'll be sending the recording of this in a week or two.
Awesome. It was my pleasure.
Yeah, thank you all.